Yeah, so this was a blog that we worked on with Stephen back in August. And we were basically sort of trying to drill down to the sort of essence of machine learning, throwing away various bits of complexity and seeing what remains. And let's just jump in. And basically, this is going to take the format of like one of Stephen's readings, but without a focus on the text and more on the experiments and what's going on in each of the click to copies. So to begin with, we were just looking at sort of learning simple functions, one dimensional, R to R, you know, and then looked at sort of simplifying the topology of the networks. So that's what kind of follows in this section here. So this is the first thing we sort of throw away is this sort of multilinearity or whatever between neurons in successive layers to see if learning is still possible. And that's motivated by the kind of locality property of this kind of a network. So if you think about sort of a fully connected network, you now in hardware or in electronics, you have to somehow sort of route all of these connections. And the brain being some three-dimensional thing doesn't have much of a problem doing this. But yeah, in silicon, it's a lot more difficult. So yeah, having this sort of 2D array thing is sort of motivated by that.
Just a quick
And
question. Is that diamond
yeah.
shape, whatever you want to call it,
Mhm.
deliberate? That that specific topology?
Um, well, it's really because we have like one input. And so the sort of, if you want to think about it like the causal past of this output neuron, it's sort of only you know, it's only going to cover, it's only ever going to sort of touch this one input. So, there's nothing else kind of being fed in apart from a bunch of sort of implicit zeros on sort of hidden neurons that are not really participating to the behavior of the function. So yeah, it's kind of like you need to expand a bit, but then eventually collapse to one. So um, yeah, that's why it's like that.
Yeah. Okay. So it's like a
Yeah,
maximum expansion rates kind of idea anyway.
yeah, it's like expanding to some capacity and then squeezing back. Yeah. Um,
So if you were to like put a voltage in or an amount
mhm.
up top, then you could see
Yeah,
like all the links activate or the neurons activate according to their function.
that's
So the
correct. And
activation.
actually,
So, oh,
one of
that's
one of
what
these
this is.
visualizations, let's see. Uh, yeah, exactly. This set of plots here are showing across the function domain across X, left to right, top to bottom, we're showing how the internal activations change.
Okay, so
Is boolean activations or is it um
No, these are continuous. That's coming later. Yeah.
is it possible to make a list animate in that thing?
Yeah, and I think I did whilst we were working on it, but I haven't sort of dug it out specifically for this. But let's see. Maybe I could find it. Where would that be? Neural nets. Might be in one of these. Yeah, I definitely did it at one point, but we kind of didn't end up using it. Um, Let me see. It's probably unlikely that I'm going to sort of find it by chance. Um, and it is quite subtle, unless you are careful with like the scaling of the values and things. But yeah, yeah, it would be in this folder if it's anywhere, or it might be like archived somewhere.
Well, if there's click to
Um,
copy available, I might be able to just grab it and then.
yeah, yeah, that's very hopeful. Maybe overly so, because let's see.
We don't have to go down this rabbit hole. None of us are
Yeah,
rabbits.
I mean, it should be fine. We'll do it live.
if it doesn't work in real time, we can tweet it out afterwards to people so that they've got that animation in
Yeah,
mind.
let's do it. Oh, that's not too bad. So, uh, if we just don't partition, we just do list animate. We'll do it live.
Very cool. So this
Yeah, so
isn't
there's
training or something, or what is it doing to?
sorry, your audio cut out after. Can you say again?
Is it? It's not training or anything. Is it just showing?
No, this is already trained. This is post training, and basically the slider represents our sort of x value here between whatever it is, it's going across the function domain.
That
So,
function is trained. That
yeah,
function.
so there'll be little sort of transition points where, in order to capture the behavior of the function, you'll see like large changes in the internal activation.
So I've got a question. Is this inspired by any existing architecture, or
No,
like
no,
what?
no. It as I said, it's actually kind of motivated by, if you think about sort of in the hardware, like on a sort of 2D sort of implementation, you could do this by sort of, linking up these functional units and just having local connectivity, right? When you have a fully connected layer, somehow you've got to route all of these connections like end to end, you know?
I
So
see.
like, yeah, so you got like n squared wires between two layers, and it becomes just kind of a nightmare. In 3D, it's fine because the brain has lots of area to like, and also the brain's kind of arbitrarily connected, not necessarily fully connected. But along this theme of like, let's discard complexity, this was like the first step. So discard fully connectedness. But one of the things we discovered here was actually for ReLU, it didn't perform too nicely. And I think, as I said, that's because we're sort of throwing away this multilinearity kind of between the layers, right? So we ended up throwing in the ELU activation function, but I think any kind of non-linear activation function would kind of do, Swish or whatever your favorite happens to be. It seems to be that kind of helped it. So yeah, we cut off something, we got worse performance, we made a small tweak, and then we got the performance back, and now this is something that's more sort of feasible to easily implement in physical hardware. Yeah, so that was like the first thing we did. Yeah, and this is showing the behavior of networks of different size. So at some point, it's kind of like the minimal size necessary to capture the behavior of the function. And it's particularly difficult because this one has these sharp discontinuities. So it's sort of, it tries its best, it does a bit better, better still, and then by about here, you've kind of got it.
Okay, so this is with the activation function. The
This is
sigmoid.
with it's called ELU exponential linear unit,
Okay.
but I think it doesn't really matter what specific activation function, just that it's not linear. Yeah.
I wonder what these things would look like without the um, activation function. If it was just, as you say, a bunch of linear functions pushing through.
Yeah. Those were more difficult to train and didn't produce sort of good results. So yeah, Stephen comments here that they didn't seem to work well, so we're using ELU. And I think that's just because you've thrown away the fully connectedness. So now, yeah,
Mm-hmm. What? So,
yeah.
but those up there, those were just linear combinations.
Um,
Just a lot of multilinear functions stacked on top of
the
each other.
the yeah these in this case here, it's multilinear. Yeah, it's ReLU. Piecewise linear is the activation function.
Mm-hmm.
It's fully connected and so on. And this is fully connected, but with ELU, right? So you can see how it sort of shapes the output.
Do the activation
Right.
functions allow for choosing the domain of influence for certain neurons? Oh, I want these neurons to be relevant at this piece of the graph, and then these are, so you can kind of build it up piece by piece.
Not really sure specifically what you're asking. What if you want sort of to actually precisely control what activation function is used on which layers, or yeah, if you could.
No, all have the same activation functions, or
Mhm.
like the ReLU or what have you. But if 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 the influence of a certain neuron or group of neurons is localized in the graph.
Mm-hmm. influence.
Yeah, that's part of the issue here, is because they're not fully connected, right? So for each
Yeah.
neuron, it can only affect kind of two neighbors,
Yeah.
in a forward direction.
Right. I mean, and the other thing is, I think it's kind of related to the XOR problem kind of issue where, if you're using just linear activation functions, that you're sort of restricted in what kinds of functions you can learn.
Interesting.
So I think, yeah, so I think it's kind of,
Is that like a well-known thing?
yeah, this is like neural nets 101 kind of thing. If you want to classify you want to model a function like this, you can't do it by one
It's
separating line.
two to the left. I think it states the whole problem there. XOR can't be calculated by a single perceptron.
Yeah.
So the logical concept of an XOR operation, okay, has to have
Yeah,
a multi.
but like for example, in this case, it's like, well, we've got some decision boundary, but it's also talking about the fact that the function is, it's like by being linear, it can only sort of map things in a given way. By using sort of non-linearities, you can be more expressive. It's not really a great way of saying it, but yeah,
Interesting.
you get a lot.
Yeah. So that line, if it crosses through 0, is it activating all of them or none of them?
I mean, it's basically saying when your input sort of puts you on this side of the line, then your output is 1, and if it's on this side, then it's 0. And in this case, you can't do that with a single line, right? You need 2 lines or
Yeah.
something more sort of complicated.
Yeah.
Yeah. So I think that's kind of why it's necessary here. All right. The next section was on CAs, and yeah, this was kind of a conversation I had with Stephen, in which I kind of mentioned my interest in the past on genetic algorithms and genetic programming, and it was something he sort of expressed that he thought about trying, but thought it kind of wouldn't work, so didn't bother. But then we sort of did a quick experiment, and he's like, "Oh, it actually works," and so he's been having fun with that, and the biological evolution blogs kind of that he did with Brad are basically developing that really a lot more deeply. So with this kind of model, you're sort of making single point-wise changes to a rule in order to achieve a certain behavior. Let's see
Are you
here.
determining which change to make?
Oh, just randomly. So it's like, a piece of radiation came in and flipped flipped a cell and in this representation of the rule. And what you're doing essentially is just kind of guess and check. So you're sort of like, well, let's try this. Did it improve things or did it not? And you accept the improvements and reject the failures, basically. So you get these kind of progressions where if you want this thing to live exactly 40 steps, which is a lot harder than you would think, it's not, you can't just pick a random rule out of the trillions upon trillions of rules and expect to just get that behavior. So to do it in such few steps is actually quite surprising. So you start with some random rule, or I think in this case it's the 0 rule, right? And you get this behavior. And actually, this is showing you successive breakthroughs. So there are many changes that are happening, but then when we made an improvement, we got this guy next. And we try a whole bunch of stuff, and we found this guy. And when we're trying, sometimes we do worse. That's why you see these red dots below the line.
Okay, so do you never go down to go back up, or is it just because of the graph it makes it look like it's
like a ratchet. So it's like you can't go back, you can't turn it back, but if it's being turned, in the correct direction, it will accept the change. So we're just rejecting anything that's below the best so far.
okay? But is this now just like raw enumeration, or is there some kind of
No, it's not. It's not raw enumeration. You're kind of
keeping the
you're keeping the best one and sort of branching out many times from there until you're sort of putting out lots of different feelers until one of the one of those probes gives you back a good result, and then
Yeah,
you take it,
it'll be-
yeah, take a
it'll-
step in that
it'll
direction.
be- No, it makes sense. It's just the thing is like with local minima there, how are you avoiding some like really strong local minima?
That does come in at one point, and yeah, I've got things to show about that, and
Okay, let's
some
go
thoughts
on
and
that
ideas
first.
about
Sorry, I just
yeah.
thrown all my ideas at once because it's really interesting.
No, it's
How are you,
okay. It's very relevant actually. Yeah, and
how
it
are
is
you
a
stopping?
problem.
How are you stopping like permanent what's it called? Um, just things that don't end. So just like it just keeps going forever. Are
Oh,
you reject?
so if there's a kind of maximum bound that we evolve the CA states, and beyond that, we just consider the loss to be like, we yeah, um, we actually just
Okay,
returned like infinity or something for those cases because
okay.
it's like so
So
bad that
the test is within this bound, which gets you the closest to the bound, sort of thing.
yeah,
Okay.
which gets you to sorry, within the bound which gets you to the target, which is 40 in this case. Yeah. And these are different examples, different evolution runs with different random seeds that end up in sort of different solutions. So there's many solutions, many different starting or many journeys from the starting condition to an acceptable solution. And it just happens to be that this lost surface, if you want to call it that, doesn't have, you know, um, prohibitive prohibitively many local minima that you can't escape from. But as we found out with other problems that other tasks, I should say, that becomes an issue. So yeah, the point you raised about local minima is very relevant, and I think something I've tried to kind of mention a few times is that in biology where you have sort of like pair sexual reproduction, it seems to be that that's kind of a strategy that biology uses to sort of overcome that among many other things. um, it allows it to explore not just these orthogonal dimensions of this space, right, or directions I should say, but it also lets you kind of build up momentum in some loose sense, which
Mm,
in machine learning is kind of one way that you avoid these local minima is you sort of by having momentum the ball can roll past the thing and get
yeah.
to a better point. Yeah.
Mm, that's
Yeah.
really interesting. Hmm.
So yeah. um right, so that was on CAs where we had like a global rule, so like your law of physics, basically your sort of all pervasive thing that applies everywhere. But then we tried this other model, which is where we, at each point in space, we have a different CA rule and see if we can use that to um, induce some behavior, some desired behavior. So again, for this problem of lifetime, like live a explicitly specified number of steps, we get something like this. So yeah, here's your infinite growth thing, right? This one went for forever and would go forever, so we just give it infinity.
Yeah.
Um, and then you've sprinkled some random mutations and you got lucky, and now the thing stopped there. So we got to score 6, and as we keep going we see that it's progressively building up this thing which eventually hits this target line, and you know gives us a loss of 0, or our best fitness, or if you want to call it that. And here's the evolution graph, and again showing different runs. So these are all um, winners of a different kind. Um,
So maybe can you just talk about what you mean by so okay, so maybe some simple questions. This sprinkling of kind of the purple
mhm,
uh, rules here.
yeah,
Maybe can you elaborate a bit more? What exactly is
right.
the
So actually, what you're seeing here is kind of the accumulation of mutations between successive improvements. So there are individual mutations that are happening, and that's along these flat plateaus. So anytime the evolution process is kind of plateauing, you're sort of exploring the space around the previous best solution. And
Okay.
then one little extra change got you got you an improvement, got you to the next kind of
Is this like an
level set.
evolutionary path?
Say again.
Would this be something like an evolutionary path?
Yeah,
This isn't the actual CA. This is the path that ACA has taken in a evolutionary space. In a
yeah,
space.
but the difference here is we don't have one global rule. We have a sort of spatialized situation where the rule is different at each point in space.
Got it. Yeah, that's really cool. This
Yeah.
is kind of like a Wolfram Physics project exploratory concept. You know,
And what rules are present here?
Right. For this one, let's see. 4 and 146. Which is
Which
it's been a while since I looked at this. How do we? Oh yeah, it's Boolean function 4 2. Is that what you do? And then you say like DNF or something that will give you. Or maybe ANF is better.
one
Algebraic
and
normal
two
form.
or two.
Yeah. So this one is 1 and 2 XOR 1.
Mm-hmm.
And this is 1 and 2 XOR 2. I'm very silly and almost swore. It's sorry, these are 3 arguments, so the functions are a bit more complicated.
Mm-hmm.
Yeah.
Quite a bit.
And
So it's taking in binary values, like a cellular automata. Each square looks up to its like 3.
yeah, exactly. The neighbor on the left is 1. The neighbor in the middle is 2.
Uh-huh.
The neighbor on the right is 3. And okay, ignoring slot. There's probably a better way of showing this function. Ignoring
Well,
slot.
you can just apply it to X, Y, Z. I think.
All right. Oh yeah, thanks. And then do expression tree.
Yeah.
Nice. Okay. Makes sense. Get rid of the slot. Yeah, there we go. Or we can say like left, middle, right, or something like that.
Mm-hmm.
If that is clearer to people to see what the function is like. And like, I don't know, like rule 30, the famous one is something like that. Left XOR mid XOR right XOR the AND of mid and right. Oh, but usually it's I thought it was written much more simpler than that. I always see the example here. Yeah, P, X, or Q, or R. I don't know why we're not seeing that when I. But whatever.
Try EOF.
Ah, thanks. End of file. Huh?
Maybe I'm confused.
Yeah.
I got it from memory. Maybe Boolean convert.
Ah, right.
Oh, ESOP. I remember that was S. E there. ESOP maybe. No, that's still no.
Yeah. Yeah, it's just giving us kind of like more than I would have expected. But actually, what about just doing is there not Boolean minimize? Is that? Huh. Well. All right. Form. Yeah. Boolean minimize. Should take
also
that form.
my resource function. It actually links, the documentation links to it from the Boolean convert. Called find Boolean alternative.
Ah.
So you can list this Boolean function and just provide whatever functions you want. And it's just gonna brute force.
Ah, cool. Okay. You said
Is
it's
it
called find Boolean.
Find
I
Boolean.
don't see it linked.
Well, it's a resource function. Well, for me, documentation also includes repository functions. Maybe it's a new thing.
I guess I'll just do it like this. Arguments are just the function.
Yeah. And then a list like XOR and OR, right?
Yeah.
Maybe it will work.
Yeah,
Mm,
that's it.
okay, cool.
Excellent. Cool. There we go. Very nice. Okay. Nice. So, okay, we've got a simpler view of the actual functions we're using. So we can do that for 4 and 1, 4, 6, which was Dugan's question about the CAs that we're looking at. So let's give this one a sec. It's crunching away, finding the alternatives. That's a lot nicer. It's a lot more interpretable, and yeah. Okay. Let's continue. Let's see what we. So yeah, the next thing we did is we went to CAs of the same setup but with radius a half, which look like these hexagonal grids. So it's almost like that local network that we had above. These are, we call them rule arrays. Yeah, different rule at each cell. But because we're using only 2 inputs for each cell, now we have, fewer functions, only 16 functions to choose from. So like if we use AND and XOR, we get, this kind of behavior. And you can actually kind of compose these different small patches of rule arrays in order to implement various different logic functions as well. So with a set of universal functions, you can sort of build. Actually, in this case, we can only do all the even functions, so we only get 8. But if you use a different set of rules, you can recover all 16 2-argument boolean functions. And we learned these by using a SAT solver, basically, that just kind of the satisfiability instance represented the actual rule array rather than evolving them. And we did that in order to kind of find the minimal case. So these should be, unless we made a mistake, these should be minimal. So it shows that you can build so that sub patches of these things can effectively implement like different functions, and they can be sort of composed along the grid.
So this is really cool. So you're kind of like
Yeah.
exploring an evolutionary path that effectively composes a program.
Yeah, that's right. It's program induction, but by some sort of stochastic means, and you're just composing functions basically. Yeah, that's right. Let's see here. Yeah, lifetime. But then we shifted to a kind of slightly more interesting problem, which were back to that sort of square wave function that we had, except what we do is we kind of position encode the values, if that makes sense. So it's kind of like we're using like a one hot encoding along the width of this thing to represent values. So if you input a 1 here, then you're saying -3. And if you get a 1 here, then you're saying that the function is giving you a 1. Right? That was just like one idea of something to try.
Wait, so this is like f of -1.2 equals
Something.
+1.
Yeah, exactly. Yeah, and on that little square wave function that we had before. Yeah. So we're like reapproaching that problem from above that we did on neural nets, but instead trying to do it with these discrete rule arrays. Yeah, so then we get it seemed to work very well, although this particular one sort of has a failure for one of the cases. But if you evolve for longer or from different initial conditions, you would likely find like an acceptable solution.
So
Yeah.
can you just talk about the search for that solution that you had there? Is this also just like
Yeah.
bit
All that
flipping?
changed was
Yeah.
all that changed was the loss function. So the loss function takes care of providing the network with the correct inputs. It does the evolutions and then scores the outputs. and gives you some numeric quantity back, which you can use to compare two things and see which one is better than the other, basically.
Oh, sorry, maybe
Yeah.
I was misunderstanding. So, okay, so this is just is this the best result? The distribution of the orange and green here was the current result, but when you're actually training that space, I don't know what the best words are there.
Yeah.
Exploring the space, are you kind of like okay, so you progressively, yeah, actually, I don't know, how would you go like from step, what would be the steps to get to this?
You would have
Yeah.
to
So
test each candidate for its how well it performs at this task. When you
yeah.
move the top thing, how well does it affect the bread thing at the bottom?
Yeah. That's right.
Yeah,
And
just search
and
the
in this
entire
case, we start from like this uniform condition, but you can start from random. It doesn't really matter all that much.
Then are you only changing the progressive, like the further it get? Yeah, that's what I'm trying to understand, because all of those terminate or they get to an end result. So then how are you deciding how to change the orange rules or the direction? Or is that just the whole space and then you're just changing the direction that the thing takes?
So you just make
Right.
random changes, and you ignore the ones that are not as good as the current solution, and you keep those which are the same or better. So you're kind of moving around this level set of solutions which are of equivalent or better fitness than the best so far.
Okay, so the thing that was trained was actually the path, not the space. Sorry, maybe that's where I was getting confused. The space stays constant. The green and orange is like the space of
Yeah, like the dimensionality of this thing
okay.
doesn't grow or shrink. I mean, you could do
Oh,
that, but
that's the entire dimensionality. Okay.
yeah. So it's like, you make a neural architecture and you fix it, and then you train.
And okay, and then
And yeah,
at every moment you can choose for any given input, you can then progress through that space by either going left or right.
well, we compute the fitness over all possible inputs and build up a score based on how it performed across the whole range. Right.
Okay.
So the
Can you
loss
list
function.
the list animate of that one,
Oh, this
if it's possible.
possibly. Yeah, I remember these are quite slow. These are quite slow to render. But in the spirit of if it will do it live.
Yeah, I was just thinking that must have been like quite a large search. Like it just
Yeah.
seems like a lot of,
Let's see. These we ran
space.
for 50,000 steps. So this is the training code. When you do the C2C, you get the training code, but we've commented it and we use a cloud import, so you actually can just not wait for however long that takes. All right, and it's the rendering that was pretty slow, but let's see. Let's see what it does.
While that's doing
While it's
that,
doing that, yeah, we can.
my question is,
Mhm.
you said that there's potentially a solution, like a full solution there. So you didn't run an exhaustive search on every possible path. Is that correct?
We did multiple runs, but here we're just showing one run. Yeah. I mean, and the other thing is it's kind of alluding to like these solutions sometimes are approximate. Like for like again in neural networks, you're not always getting like zero loss, you know.
Yes, yes.
It's not, yeah. When you train like a GPT, you're not getting like exact zero loss. You kind of don't even want that to some degree. So it's speaking to like the sort of approximate nature of these solutions. I don't know what this is doing. What is it doing? It's probably getting like the resource functions. Anyway, let's just kind of move forward and we can look at it if and when it renders. So this is the behavior of the function across the domain. And you can see the one little missing point that was indicated above with no result. And this is decoding that positional encoding. So like just turning these back into their numeric form. This is a plot that's showing apparently evaluation completed. We got it. Okay, now we have to sort of like list animate that. So I guess get rid of that, and change that to list animate, and get rid of like that. Let's see. Yeah, this is kind of giving you a sense of the mutations which accumulated between these successively improving solutions. It's just a different kind of view on that. Here we go. Oh, this is cool. All right, so 0, 1, 0, 1, 0, which is the function that we made up. Yeah, I'll just let that play a couple of times just to give a sense of how it's.
Can you slow it down a lot?
Yeah.
Because the frame rate on Zoom is not.
Yeah. Okay. Yes. When I click slower, it goes faster. So I'm just gonna do it like. Okay. It's okay. I'll just do it manually.
So my question is, what's the chances, or what's the potential that no path exists between that not found?
Well, it's difficult to say without actually trying. Like you know, and it depends on the choice of rule, the particular loss function, your initial condition, and you can't know. It's like an irreducible thing. You can't know before you try. Just like you don't know what the weather will be tomorrow, kind of thing. You can't know, ahead of time. So, but some problems are easier than others. Some have clearer paths. Some have loss surfaces which are sort of better behaved. It varies basically. Yeah. But yeah, it's kind of cool. You can see that across a range within that function where the output value remains fixed, you can see that, for example, here these two inputs have a lot of the state evolution is the same. They kind of only change in this top portion. It's kind of interesting. Yeah.
Mm-hmm.
Yeah. But it's just found a way using the rules that it has been restricted to sort of implement this function. And sometimes the ways it does it are kind of clever, or or it looks clever, but that's like intelligent design. It sort of looks like someone designed it, but it just happened to come out that way. Here was some sort of analysis of like the various densities of the activation, the individual state for all possible inputs, including inputs which are invalid and so on. So I don't know.
Okay, so that kind of like helps me think about this as well. So remember at the top, you said that when you were searching for what rules get you to 40, the best, you kind of it's like a wrench-like behavior. So you get to the highest one, and then you search from there for the next highest, and you proceed like that. So is that not what's shown there with that density plot?
Well, the density, this thing here you're referring to, or
no, sorry, that exact
this one here. Yeah, I mean this is showing that
the first one there was maybe a bit of a delay. This one over here exactly. So there's a diffusion at the start of potential starting. Oh, but I guess you have to because you. No, sorry, this is obvious. Never mind. Yeah, it's kind of obvious because you only have two outputs that you're trying to get to.
Yeah, I mean it's nice because you're seeing like the concentration of the activity of this thing sort of start to focus on those valid output values.
This is what I wanted to see. So how you actually.
So this is the state density over the evolution history. Yeah, and it's computed over like a large sample of possible inputs, including invalid ones that are not of this one hot encoding type. So like 101010 wasn't in the training, but we can input it anyway and see what it does. Right. So yeah.
So my question here is that this isn't every possible.
No, this is a straight line path. Yeah, like from dumb to evolved. And for example, this one you can see there's a lot of activity around here, but it's useless because it doesn't help us in sort of getting the final solution. Yeah. And this is actually all possible inputs. So we enumerated all possible.
A very interesting picture actually, because basically what it's saying
Yeah.
is like, one of these statements are intelligence is something like your ability to handle like more entropy or something like that, or like evolution happens because you can handle more and more different random inputs. So this thing is evolving to handle every possible input and still kind of survive in a way by getting to
Yeah.
an answer. Yeah.
It's kind of equivalencing things and paying attention to what matters. And by identifying features and so on, you're kind of seeing the world as you want to see it in a manner that's beneficial and contributes to your survival. I guess it's like, what's his name? Donald Hoffman's work.
Very cool.
Yeah, so let's see here. This is another kind of density analysis type thing. Let's see. Yeah, looking at basically tallying up the different kind of outputs that we get and what initial state led to those. Don't really know how interesting that is. This is about corrupting the initial state. So in this particular instance, it wasn't very robust to corruptions of the initial state, and that's really just to do with the choice of rule. In this case, for this particular problem, and it's an aspect of the encoding. So the encoding is quite fragile, both the choice of rule and an XOR. Because if you put another cell active next to this, then an XOR will give you 0, which you might not want, and so on. So yeah.
So why are you
But
adding corruption, or what is the corruption?
we were just exploring, like, if an input is somehow corrupted, if there's noise in the system, or the world is a messy place, kind of thing, does it still behave in an acceptable manner?
Mess with it a
But
bit.
yeah, I don't really know how sort of significant this is. It really is a statement about the fragility of the encoding and the choice of rules, the two rules that are being used in this system.
Is that analogous to some other concept in machine learning, like initial weights or like training too?
I mean, I guess it is. I mean, it's like, if you look at language, there's a certain degree of robustness in language. You can scramble up all the middle letters of words, for example, and still make perfect sense of a sentence. If I was to randomly shuffle all of the letters in the middle of all of these words, you would still be able to read these sentences. But if you corrupted the first and last, then and completely set them to something absolutely random, then it might just fall apart. So I think it's related to like that.
Yeah.
But this one hot encoding and the choice of rules together contribute to this thing being quite fragile. But it's not necessarily the case that this particular approach is always going to be fragile. And you sort of wouldn't want it to be. Depends. Let's see here. I don't think these are particularly interesting. We're just kind of looking at the sort of evolutionary tree. They weren't looking as diverse as we'd kind of thought. They're kind of difficult to generate, and and for the lifetime problem, they don't produce very interesting graphs that have like a lot of branching and so on. And for other problems, you kind of just have to pick a random place and explore the neighborhood around that. And it becomes a bit tricky. So I wasn't really satisfied with the results here, but you get the sense of like a tree of life kind of thing happening, where each level is an improvement, and there's a sort of a branching
So
situation here.
in a more ideal way that this would have, you would have been more happy with this, would it have shown what, like just a wider selection of evolutionary paths?
With kind of independent branches that are not necessarily sort of connected. it's just a bit tricky because you some of these were generated like exhaustively, so we were looking at all solutions around the neighborhood of this thing. So it was a bit slow. And then rendering these, when the graphs get large, these become hard to see. So it's kind of a practical visualization sort of bottleneck thing. But and then I think the choice of problem, the lifetime problem, and your choice of rule don't necessarily lead to interesting trees of life.
Yeah, so
But for other, mm,
that was my question, because what, like, if you had to do the tree of life
mhm,
multi-way system for getting to the end result, so not the length, like going back to the original problem of this piece,
mhm,
was, you know, getting
the
the
lifetime.
correct
Yeah.
output. Not,
Mhm.
yeah, just of this section. I mean, what would the multi-way graph of that look like?
Um, let's see here. I mean, quite messy and uninterpretable, but you would hope that those terminal nodes have a lot of sort of disjoint sort of sub trees, basically, or sub
Mm,
graphs, right? But they do share some sort of common ancestor and sort of branching and merging and so on.
just
Yeah,
yeah, that's a good
it
point. Like they'll be kind of uninterpretable.
yeah, it is kind of practically tricky to do. But I think, yeah, with some pruning, that was something we were thinking of doing. That would allow you to show larger rule arrays, bigger graphs, but you sort of prune out some stuff to kind of still communicate the idea. And that's something that, yeah, could do with some more exploration, I think. But yeah, the general idea is that you have this sort of diversity of different ideas, and those ideas get developed and built upon, and they are distinct. But they, yeah, independently lead you to an acceptable solution. Just as life has these different sort of evolutionary niches. Yeah, sorry, one sec. All right.
Yeah,
Yeah. Okay, let's see. So this I think is going to get kind of interesting. So one thing you could do is like exhaustively mutate every cell independently and then color or indicate whether it made an improvement or made things worse. So these plots show you that for a given problem, which in this case was, I think we're back to lifetime here. Lifetime problem, live a fixed number of steps. You can see that there's this kind of front that sort of grows on the thing where I think we indicated red being an improvement, blue being a step backwards. And yeah, so it's kind of showing you that as you're building something up, there are things that get locked in. If you were to mess with them, you would kind of ruin your solution and go backwards. And you can see this thing kind of drilling progressively towards the final solution, which is here, which can get no better because it's already solved, and that's why you don't see any red. Yeah, any
so,
thoughts or
so
things on
why
that?
is the red disconnected? If you go three from where you are to the left,
It's just
where
yeah, so that's basically saying like you could make a mutation here or here and still make an improvement. You're not restricted to like one little patch, um, if that makes sense. So it's a bit tricky to see because we actually have to see the rule array and the state evolution, and we're not seeing them kind of overlaid because it'd be quite
oh, they're not
confusing.
overlaid. Okay. Yeah, I
Yeah.
get it. It's just the
I think
space of where things are adapting in the environment of sorry, in the space. Yeah,
yeah, it's basically
like
showing
heat map
you
kind of thing.
which mutations are beneficial and which are detrimental. Um, yeah,
'Cause
and the
if you, because it's only the ones that are nearby where the thing is trying to drill down that
yeah,
affect it.
right. But there is an effect earlier up, but it's a
Mhm.
corruptive effect that's screwing up the evolution further down. So that's why this thing has a bit of yeah, like a locked in part of the solution that you can't mess with because you'll just go backwards. Uh,
Yeah, you'll send that river to some other place if you
yeah,
do
yeah,
dam of it, uh,
yeah, or
or
you'll
some
just terminate
obstruction.
it, or yeah, exactly, yeah. Yeah, so that's kind of cool to see, and it relates to what we're going to discuss.
So it's like curling.
Yeah, I guess it's like sweeping the ice and trying
in
to
front
clear
of one of those things.
Yeah, and there's some relations to things like percolation that we studied for a bit as well. You're kind of trying to clear like a path. Right. Sorry, I need to clear my throat. And have a quick drink off mic. Okay, so now this thing here is actually doing like a steepest descent thing. Let's see if I can run it so we can get a better view. Better in a new notebook. New notebook, paste. Let's see. So yeah, this was using this steepest descent thing. So it's not using evolution, but just showing what the path to the goal would look like if you kind of always pick the best. After doing an exhaustive search, this might be actually quite slow to run, so we'll kind of leave it in the background. And for this particular pair of rules, it actually did something kind of interesting, which is like building this little V shape. Yeah, which was quite cool. Let's see here. Right, and so we're back to the 101 function, not lifetime, and doing the same sensitivity analysis. So you can see this green-red view on things.
When you say steepest, is this like what do you mean by steepest descent, and how
Right.
you...
So this would be the equivalent of. Let me think of a way of describing it. Instead of doing like stochastic gradient descent, you're you're basically just following the gradient exactly.
Yeah, you're incentivizing it to get to the endpoint.
More greedily, yeah.
Yeah.
Let's say, yeah. A more
So
greedy
these
solution.
diamonds, is this the space? This would be the space of where you could go.
This is the path it took, and at each step, it was always building like a cell to the left and right, and building up this kind of diamond shape to achieve the lifetime target for this particular rule pair. And it just so happened to be that the greedy solution starting from this uniform initial condition happened to be this little V shape. So it looks, yeah, kind of not organic and chaotic like the other solutions. Yeah.
It also looks like the least steepest way to get there.
I mean, it does have a lot of steps, but that's just, you know, each step is a breakthrough because we're doing an exhaustive search. We're not it's like we're not wasting time doing mutation searching randomly. We're searching everything and picking the best. So yeah, it is an equivalent amount of work. You're just seeing more breakthroughs because yeah, every mutation or every step is a breakthrough. Okay, it has done it. Now it's just plotting our favorite formatting notebook contents appears. And let's see.
So how... Yeah,
Let's do a
maybe
list animate of that.
on those so we can actually see.
Let's do a list animate. I am also a fan, as is Dugan. But unfortunately, the animations never make it into the blogs. That's why I never leave them in. Oh no. Okay, wait. I'll have to
It'd
zoom
be
the
cool if we
page.
could get something like GIFs into the blog or something where you can actually get the animation.
Yeah, Stephen once sort of mentioned that he was sort of open to it, but I think he prefers not to have. You know, when people are reading, they don't want like stuff moving. But I mean, with a play button, it might not be too bad. But yeah, there you go. There's. Sorry, it's not so clear. I did magnify it, but there's probably a better way I can do this, like another function. But yeah, there you go. There's your steepest descent learning, achieving its target. All right. Okay, so now we're getting on to essentially the whole topic of like back propagation. So like looking at a neural net, you can make these sort of infinitesimal changes and look at how the function behaves, right, around the neighborhood of a particular network configuration. So you can see this kind of function space effectively when one changes a particular, yeah, dimension or parameter. So that this is the behavior of the network as this weight is changed, as this weight is changed, as this weight is changed, and so on. And these are very nice plots.
Is that a wild idea? Do you think backpropagation is like sexual selection?
Um, let's see here.
Because you've evolved something, and then you can go backwards from that evolved state to be like, yes, like you. It's like you're choosing from a result if this thing is what you want, not kind of progressively. Yeah, I don't know. It's kind of a wild idea.
I think the thing about like, you know, because essentially with what we were doing above, it's kind of like asexual, right? It's just like a single organism that's mutating.
It dies off every time it gets it wrong.
But you're only able to sort of explore one dimension at a time. Now, what happens with like a sort of family tree or like the family tree of the human race is now you can sort of pair up things in sort of distinct areas of this tree, which might have made independent, successful changes that combine well. And so that's kind of a discrete approximation of this partial derivative. But when you're only sort of independently changing individual sort of orthogonal directions in this space, you're kind of restricted, right? Because there are n number of single dimension changes, but then there's some other number of two like pairwise changes, or if you wanted to change three things at a time, there's all sorts of ways in which you could change three things, and it becomes very challenging to sort of explore that together. I mean, so we're doing like one mutation. You could choose two at a time, but that might
Yeah,
that might be
yeah.
prohibitive, or you might pick a random number of mutations at a time. Like sometimes we make one, two, or three based on a dice roll. That's something
Yeah.
I've done.
I don't know. It's just kind of a wild idea.
But
Also, backpropagation is the least sexy part of ML, so it's probably not that.
right, but we're about to talk about it. So this plot, which is courtesy of Nick, is really cool, and it's showing us this function space sort of in the locality of a particular change on a particular weight of this network. And yeah, I think it's a really nice view on what's going on. So yeah, right. And now you can make sort of like combinations of changes, right? When you're adjusting a network, you're actually adjusting the whole thing all together, right? So you're sort of you're able to sort of move in sort of combinations of this whole space. Now, yeah, now we're going to get to right. This is a description of effectively the chain rule, right? So as you compose functions, using the chain rule, which is a rule that tells you how derivatives behave, derivatives of composed functions behave, and gives you a rule for sort of computing them. Right, and there's different ways to do it, and with backpropagation, we're relying on the fact that we only need the derivative, we only need the gradient from the layer above, and we only need to know like how we behave, how the function itself behaves. So each node is sort of playing its part in this sort of unpeeling of the function to compute the derivative of the whole network, all of the parameters, derivative of the error or loss with respect to all of the parameters. Right. Let's see
So,
here.
is this kind of like just abstractly talking about chain rule in
Yeah.
terms of functions?
Yeah, basically, in terms of like, this simple thing, you could imagine each of these was like a layer, like a linear layer or something, or like a linear layer and an activation function, a linear layer and an activation function. This is your input, the whole thing is your output. And so, yeah, when you perform this chain rule, or when you perform back propagation, you now have access to the derivative of the loss with respect to these weights, which are the sort of non-input parameters, right? That's your input parameter. That's your input to the network, and then these are your weights.
Okay, so each weight is affecting the function. It's like the second argument to the function. Yeah.
That's right. Yeah, that's right. That's exactly right. Yeah, and I think that's all that's really.
You guys is that just like something you guys figured out, or is this kind of like known?
I mean, it's already known, but it's like presented in a nice way and sort of in a sort of Wolfram languagey type way here. Yeah. Yeah. Let's see here. There was this thing which was quite cool. So this is like yeah, like a sort of sensitivity analysis of how let me see here, how the evolution of a CA changes when you sort of change the some earlier state, right? So right, so we're basically flipping some prior state and seeing whether it would change the value of the output. And we're indicating which locations would change and which wouldn't. And then we get onto this topic here, which is
was that
effectively
connected to back propagation in some way? Like,
yeah, I mean, yeah.
so is it a reversible? Yeah, yeah. Maybe I got a little bit lost
No,
there.
it's not a reversible CA, but what we're doing is we're making, all possible changes and then running the thing forward. It's related in the sense that sort of like by adjusting something, earlier in the history, you've got some influence on these later outputs or later computations.
What are you adjusting exactly?
We're flipping the state, right?
So that would be equivalent to a weight or something of.
That's right. Yeah, and that's exactly what sort of motivates this section. Yeah, equivalent to a weight. Yeah.
Oh, okay. So it's kind of like, let's say you
It's
have
like
rules, but you have
it's
a mesh
very
of weights that you overlay with it, and then you see what the effect the end result will
yeah.
be. Okay.
Yeah, it's like what we did here, the sensitivity analysis upon these rule arrays, except what we're changing is like the activations, not the weights here. Yeah.
Oh, that's
Yeah.
pretty cool.
Yeah, because
Wow.
when you change a weight, you're actually changing the sort of downstream activations as well.
Yeah.
Right. Yeah. So that's
Okay,
Mhm.
was this kind of like just minimally exploratory? Because you could think that potentially something like Rule 30 or 110 or whatever it is, with a series of pre-built activations on the landscape could get you to have pretty dynamic results, like even maybe
yeah,
fixed
unpredictable results, and yeah.
like, but what I'm
Um,
saying is that could you train that landscape of weights to get like Turing complete solutions and
Yeah,
stuff like.
actually, let me show you because I think it will address your question. So in this whole sort of theme of simplifying things, making things Boolean, we're sort of we're trying to throw away real numbers effectively, and so this whole situation of computing derivatives, it's kind of natural, and doing calculus and so on is sort of natural on real numbers where we have like infinitesimals and we can derive all of these rules.
Yeah.
And so on, chain rule, product rule. We can take derivatives of known functions and our activation functions and the whole network because we have the chain rule. But what we're wanting to explore next here is whether we can throw away those real numbers and compute derivatives on Boolean functions. And there is some work. There's things like this paper here and a few others that we were sort of looking at, which they allow you to sort of derive this essentially sort of like Boolean derivative calculus effectively. So it's giving you an idea of whether a change in an input would result in a So for example, if I flip this one black and the output goes black, that means they're sort of moving in the same direction. So that change is kind of correlated. So you would think of that as kind of like a positive gradient. Whereas if I flip this one black and the output became white, that you could think of as a kind of negative gradient. Or you could call this a true gradient and false gradient, whatever you want to call it. So that's the idea, is that you can compute the partial derivative of a Boolean function with respect to one of its arguments, and what you get out is another Boolean function, right? Which is telling you whether the thing would change in the same or some opposed direction, or not at all. Actually, there's a kind of three-valued thing going on here too, but you can kind of ignore that. So like, for example, the identity function, right? It's like, if I change my input from false to true, my output also goes from false to true. So the gradient, you could say, is true, right? And if I have not, and I change my input from false to true, then the output goes from true to false. Then you could say that the gradient with respect to x of not is false, and so on. And you can do this for like all the Boolean functions and build this table here. For the two arguments, you get a different function for each
You
argument.
mean when you say it's true, you mean it's a function that constant true?
Yeah,
right?
that's right. Constant true. Yeah, that's correct. Yeah. Yes, it's that's important. It's a function true. Whereas for XOR, it's a function of not y. So the partial derivative of XOR with respect to the first argument is not of the second argument. And yeah, as you point out, it is a function. Yeah.
Oh, because okay, the x.
Yeah.
Oh,
Yeah.
okay.
So it's pretty cool. So now we've got this like table of Boolean derivatives for all possible functions. So like for any one of these functions, you can just look up which corresponding function represents the partial derivative with respect to the first or second argument. And yeah, we derive this table here, and there's kind of these functions effectively let you compute these. Okay, let's see. Right, and just as we have like the chain rule in traditional calculus, in Boolean derivatives, the chain rule ends up just being XNOR, which is effectively just equals. And what it's saying is, are these things moving in the same direction, which is kind of interesting. So it's saying it's basically saying, is the derivative of the inner function moving in the same direction as the composition of the derivative of the outer function at the x of the inner function. So yeah. So we have two functions, a and b. We've composed them. We've got b of a of x, and yeah, the partial derivative with respect to x is actually XNOR. So this gives us a kind of chain rule that we can use to propagate through some Boolean function and compute the derivatives. And that means we can avoid this, in some cases, we can avoid this exhaustive thing where we have to mutate every individual cell. And instead, we can just propagate the errors backwards through the system, even if it's a discrete one. And we demonstrate that with this plot here. So the above plot and below plot are two different things. One of them is the sensitivity analysis that we did above, and the other one, I think it's the lower one, I can tell you. So one of them is computed by Boolean differentiation. The other is computed by exhaustive sensitivity analysis. You can see they're not exactly the same. So there's some degree of error going on here, or approximation, because there's like ambiguity in some cases, or some things are not so neatly differentiable. But let me tell you, sometimes things don't copy nicely. Yeah, the bottom one is the backprop, the top one is the sensitivity analysis. And the fact that there's like close correspondence here is kind of encouraging. And I have a concrete example where we sort of show it in action. Let me just pull that up. rule array backpropagation, and let me see. I think it's this one. So this code is basically doing the full chain rule backprop story through the whole rule array. And then I show you the learning process. So let me see. It's just loading in stuff if you give it a second. Right. Yeah, so this is actually showing this is showing you the learning process taking place. So these are the gradients. These are the gradients with respect to the rule and then with respect to the inputs at each cell. And when it reaches this white condition at the end, that's showing that the learning is complete. There's no more gradient, right? So you can see there's kind of some jiggling. Why is it stopped? Yeah, so you can see some kind of jiggling, some and at each point we're flipping a rule cell, right? So we're making a change and then we're recomputing. You know, just as in machine learning, you make a change in the parameters, then you take another input mini batch, you compute the forward pass, then the backward pass, and you take a step and repeat. We're doing that same thing here, but on rule arrays. This is just trying to learn like the identity function. So like just copy the input, right? And this is so starting from some random thing, you can see that there are errors. So it's wrong. It's giving like no value where there should be a value, or it's giving values where there should not be a value, kind of thing. And this is showing you across the whole function domain, right, for every possible input cell. And if we play it, you can see if it's not going to stall whilst it's caching things, yeah, which it could have done ahead of time. You know what? It's always better just to use the slider. You can see that over time, it settles into this nice organized thing at the end. So, boom, and then we get our, yeah, so it settles into this nice picture here. And these are rules, right? So I forget what they are, and an XOR, whatever it happens to be.
Is that what the purple and the green is?
Yeah, those are the different CA rules that are being selected at each point in space. So this picture is showing like we can compute the gradient of the rule and the gradient of the input to that cell and propagate them back, you know. And that's giving us a
that just true or false?
Yeah.
Left or right?
Although it's because you're accumulating across all possible inputs, that's why there's not just sort of, you know, hard blue, hard red, right? You're sort of tallying things. That's why we see the light and dark shades here. But that's the only reason. So yeah, it's showing that you can do backpropagation in a discrete system. You don't need to exhaustively search every mutation. You can identify candidate cells that you might want to change and can make a kind of more straight line path to your solution. So we're not using random mutation. It's more informed, you know. But we're not doing this exhaustive thing either, which is inefficient because we have to change independently each thing, which is costly. So yeah, it starts in this like random initial condition, like a randomly initialized neural net, and it ends up in this very ordered thing at the end, which is a solution to compute the identity function. Yeah, and there's like more things here. Yeah, that was just me figuring some stuff out. Yeah, so yeah, that kind of concretely shows you a demonstration of this Boolean backpropagation thing in action. And yeah, I don't know if I want to sort of explore this lower section here so much. This is again this story of like what of universality. Like, can we cover the whole space of possible functions by just using some universal set of gates and yeah, that's a kind of known result, but can we find it And
Uh-huh.
again, we used sat solver to find it in these cases. And in one of them, we used mutation, so we end up with some crazy thing. And this thing is quite cool because it's generic. So you actually specify the function in these bits, in these input bits here, and then you give it some inputs, and the output will correspond to f of pq.
Oh,
So
that's
this is it's kind of like a higher order function, sort of, if you can twist your head that way.
those specific ones that you're pointing out there.
Yeah, these are in some sense like a kind of higher order function in a way, because you're free to change f to what you can provide f as an argument and p and q as your inputs, and your output will be f of p and q. F is the binary number encoding of the function index, or the function as a numeric value, because Boolean function. Yeah.
P and Q are supplied by 2 of those hexagons.
Yeah, like the hexagon that would be here.
Oh, I see.
Yeah.
It's not
And
shown,
the 4.
but yeah, they're
Yeah.
on a more top row from there. They're sort of. Oh, I see the white ones there, the white and black. Okay.
So they're yeah, it's like 2 inputs, and then I think we left a gap.
Yeah.
Yeah.
So
But you were saying
Um,
that, okay, sorry, Dugan, you go first.
right. So with 2 binary inputs, the space of possible functions on that is a set of 16. You said
That's right. Yeah.
16 different.
Well, actually, sorry, we have 3 inputs here. So there's
Wait a minute. 3 binary inputs.
Oh, so sorry, no, I'm wrong. We have 2
PQ.
inputs. I lied. Yes. Yeah. So we have 16 possible functions.
Okay.
Yeah. So there are 4 bits to specify that function. We left a gap because I think we're using and an XOR, so that bit would be quite problematic and sort of interfere with our input. That's why the gap is there.
Wait, were
Yeah.
you saying something like there's 3 Boolean combinations of 3 Boolean combinations that give you every Boolean function or logic gate? Or yeah, sorry, I missed that part.
Yeah, there's like universal sort of sets, right? And you can just do it with two Boolean functions. I mean, in the same way that you can do it just from one, right? With
Yeah.
NAND, like with NAND, you
Yeah.
can recover everything.
And XOR is the other one, right? Or was it XNOR?
I think, well, XOR and XNOR, I think, are together a universal set, but that independently they're not. Yeah. Let's see. Yeah, there was some cool stuff actually below. In this case, it's like you can only change the rows, so it's like a one-dimensional kind of situation, not a 2D thing. So it's yeah. Let's see here, and then we had these Boolean networks computing the same functions, but the weights can only be like true and false. These are learned by evolution, but they can be learned by backpropagation, which I do, and I'll show you separately. And also this other idea that came up at one point, which was like an autoencoder. So the idea that you have a bottleneck, an information bottleneck, where the CA doesn't extend into this white area. So you have to make use of this middle section to encode your input, and then recover it, approximately in the output. And you can see that as you squeeze tighter, the approximation kind of gets worse. And here we're trying to encode like the number of sort of consecutive ones that are batched together in the middle. And then we were looking at like these autoregressive models, so looking at sequences like an LLM, and something kind of akin to a transformer layer, again learned by evolution, where you're kind of computing like a probability distribution over the output. Again, it's all discrete. There's no continuous things going on here, but you do get like integer quantities sort of falling out. So if the task was to predict the future of like a sine function by passing it through this system here, which has an embedding, it has a linear layer, you can actually sort of predict the next token, as it were. Sorry. And with more complicated functions, it's harder because like for example, the sine of x plus sine of some irrational number is not easy to predict, and it falls apart in
Wait,
this.
so what's happening here?
So what's happening here is we have
left to right?
Yes, left to right. We have a sequence of like tokens, distinct things. We look up a code book, and we're using this, what we invented, like a kind of transformer layer where you can put the embeddings into this array, and each of these cells can sort of tap this array at a different point and compute a different function. So these are like the rule array cells. And the position is also another mutatable kind of quantity. So when you mutate, you can sort of, reattach this tap to a different, these red dots can move to a different location. So kind of like an attention head sort of, but it's not, but it's fixed. So if you're, let's see here. So each value of this function is assigned a different sort of bit vector, and you assemble them into this array, which then lets you kind of summarize them, and then you can use this linear layer to then compute the probability of the next token being one of the different classes. You can see that it's got like maximum.
So what is the distribution of the black and white cells on this checkerboard? I'm kind of really struggling to follow, so I'm just going to ask some dumb questions to maybe see.
No, it's all right. I could explain it clearer. So we have like a function, sine function, but we've discretized it. So it has like 10 distinct values.
Yeah.
Which means we can make like a code book. So the number 4 can be like some random bit vector.
Okay.
It's like an embedding.
For each. Okay, it's an
embedding, but it's a discrete embedding.
Got it.
Yeah. Right. So then our sequence would look something like this. So that sine wave would end up looking like this. Cool.
Got it.
Yeah.
Okay.
And then we slide this thing over that. So this window is like a kind of chunk of this that's being slid over the sequence, which would produce its own, effectively would transform this sequence into some other sequence, which could be of higher dimension or whatever. We're just kind of summarizing different windows of this sequence. And we're doing that. So
red dots?
Sorry, I had two things.
Mapping in some latent space then?
Yeah.
Before it maps back to predict the next column?
That's exactly it.
The next value. Yeah, the next column.
The next value. And it does it by predicting a probability for each token, just like you do with an LLM, with a language model.
So the red dots are the attention mechanism or something like that?
Yeah, it's kind of like not an attention mechanism in the sense that it's dynamic, but it's basically saying that this unit sort of only pays attention to like this and this. Yeah. And it computes whatever function the color indicates. And could be and an XOR, similar to the rule array that we had above. Yeah.
Okay, so you have to take the whole thing into account. That's why it's next layer it's like predicting the next vector kind of thing.
Exactly. It's predicting the next value of the function, which then gets embedded. This thing slides one to the left. You put the new code vector in on the right, and then you pass it through again and repeat. And that's what gives you these things. So given this prompt, it's able to guess like one at a time, just like ChatGPT kind of builds up the sentence, token by token.
Okay, and then that's the probability of the next one. Okay, so once you've got that space of the red dots and the black and white tiles, that's your weights of your neural net of your LLM.
Yeah. Well, these are the weights. These are sort of like the connections, and these are the functions. So the trainable parameters are where the red dots are, the function or color that's here, and whether these weights are identity or not. So in these Boolean networks, you really only have two choices, identity and not. So it's like +1 and -1 in terms of a multiplicative weight. You could think of it like, yeah.
Very cool.
Yeah, so we've like shown an example of something that's kind of familiar to all of us by now, language models and transformers and so on. But we stripped away, a lot of things. We've stripped away real numbers. And but we still have the capacity to do things like sequence prediction. We still have some way of doing information bottlenecks.
Informational bottleneck part, I didn't understand the motivation behind that part.
So that's like what's going on with autoencoders, is that you're kind of trying to summarize an input by compressing it into some lower dimensional latent space, which you can then use the decoder to like recover the input. So if you slice this thing in half, one half would be the encoder, the other half would be the decoder. And I could give you one half and I could keep the other, and you could still send me messages. That's one way of looking at it. Yeah, and I had some other things to show in relation to that. So this will be pretty cool to show. Let me see. Oh, this video is like ridiculously huge. So this is actually, if we let the video loop run, this is the training process of a Boolean network using our Boolean differentiation and Boolean backprop. The red flashes are showing you, oops, I hate how VLC does that. Sorry, one sec. Let me just make that the right size and put like a loop on, and it should not do that. And I can continue talking. Damn it. This will have to do. I think it's pretty good like this. Yeah, so that's your loss curve. Here are showing you the raw weights in the top. So you can see there's kind of some flickering going on, which is, every training step we are making some adjustments to many weights at a time. And this is a visualization of the whole network with one input fixed and showing you the activation, eventually ends up with 7 being the correct prediction. And the red is indicating where we're doing a bit flip of the weight. So we're changing it from identity to not, or from not to identity, where we're updating a parameter, right? But we can do it in
weights
this.
Are binary then too.
All the weights are binary. They're either identity or not.
Mm-hmm.
Actually, you can think of it, and it's not necessary, but you can think of it like the activation function is XOR. So you're saying input XOR weight, and it's like the weight is telling you whether, because XOR, a comma true is one thing, and XOR a comma false is like another thing. It becomes the identity or the not function. So
That's
it's basically saying
inputs, like each one is hooked up to a lot of, just more than two.
So
right?
Each neuron here is hooked up to every input on that input layer. Each neuron here is hooked up to every neuron in the preceding layer.
But the weights
so fully,
are
mm-hmm.
If a weight is 0.
Well, yeah, you can think of the weight as being true or false, or you can just think of the weight as representing a function, identity or not, or flip or no flip, yeah, however you want to call it. But the key thing that's going on is that we're able to make sort of
wait, so there's never a weight that's just the false function, the 0 function.
Right, that's correct. Yeah, that's right.
I mean, that would effectively make.
But things can let's
undo some of the links, I guess, if you nullified them.
Let me see.
And the for each particular neuron, like it's not adding up.
Okay, so right. Let me just, because I didn't explain. Right. So you have your inputs. You either flip or don't flip. You tally them. You sort of accumulate them. And then you do like a heavy side. You basically see, do we have more trues than falses? So that you could have, and there is a bias, but I don't know or can't remember if I put that here. there is a bias, but the bias is also only discrete, so it can only shift you up and down by 1 in the thing. But yeah, you're effectively just counting the number of trues and falses, and if you have more of one than the other, then that's what propagates. Right, but the key thing is we're able to make sort of like incremental progress towards, you know, the solution, and we're updating many things in parallel. We're not just updating like one weight at a time and then checking again. And you know, for this particular learning problem, it's the MNIST data set, which has, what is it, 60,000 examples. But on each training iteration, we're only taking a small mini batch. And we're accumulating some statistics as well, which, you know, when they achieve some threshold, that's when we decide to flip the weight. So there is some kind of accumulation going on in the background, but you don't need real numbers for that. You can just use integers. But, you know, you have to kind of tune or select some quantity which determines when a flip is going to happen, and that's really dependent on the network and the task and so on.
Yeah.
So it's a hyperparameter, you can think of it. Yeah.
Can I try to summarize from a layman's perspective here? So we have this number 7 written. Can you see my arrow that I'm?
I can't, but if others can, that's fine.
What if I do a stamp? Can you see this? Oh,
Yeah, I can see that. Yeah.
It's stuck. Hold on.
Oh,
Clear. Sorry. Drawing. Okay, I'm just gonna draw. So, oh wait, here's a wait. Do we have a laser? No laser. Okay, so this is a 7, right? Continental 7, whatever it is, and then each one of these blocks is like going to basically be true or false. So you have like
right.
white is false, maybe black is true,
Mhm.
and then each of these are connected to every single block of the input image. Is that correct?
That's right.
And this is trainable. So this is something that's going to change.
Yep.
And then there's another
Well,
layer.
sorry. Just the trainable part is the wires. What the circles or spheres, those are showing you the activation. So if it's black, it means there were more trues than falses. Which
Okay, this is the activation. Okay, so and this line here represents this space here, right?
that's correct. That space there, that matrix, are all the values which are represented with. Actually, I should have colored these the same colors as the light blue and purple. So you could just pretend that those are light blue and purple. That would have been clearer.
So this is
Yeah,
the
that's
input for a number. Like this is
these are the weight matrices. So those are the W's in those previous things we were looking at. Yeah.
the weights. Okay.
Yeah, those are the weights. So they're represented in this fully connected thing here, but they're represented by colors here. Just to not confuse it with the black and white for the input.
Yeah.
Yeah. Although these are effectively true and false, they kind of represent the two different functions, identity and not. So yeah.
Yes. Okay. And then you've got another layer here, which is
Yep.
this one over here, and then you've got the output here, which by this stage, it's like a combination of multiple things. That's why it's not just black and white. You can actually
That's
have
right.
this like
That's right. We didn't apply the like threshold heaviside function, you know, more truths than falses story at the end, because it's easier to train that way. That's the best way I can say it. It's when you're doing sort of like maximum likelihood learning or whatever, you're kind of trying to pull up the 7 and push down the others, and so it's easier to do if this thing is not completely Boolean at the end.
Oh, there we go. There's an arrow that's moving around.
Yeah. So I don't know if that makes sense. It's like, yeah, by keeping these things like you know, not Boolean, you have a better kind of learning objective.
So then my question here is just what informed the number? Oh, well, this number is the number you have to have because it's it's 1 to 10 of each pixel or whatever. So this
Right. So hold on. There's a certain number of pixels.
Yeah.
But these are sort of implicit neurons. These squares in the input are effectively just another set of, you could flatten this out into like how
Yes, an
you're
array.
seeing that. Yeah. So that's determined by the input specification. These are sort of picked arbitrarily. I mean, there's a certain limit. You can't squish this too much, but it's just some sensible.
So the
It's a
number, so
high.
that
Mhm.
the number of activations on that layer is arbitrary.
It's a hyperparameter, let's say.
It's a hyperparameter, and that's this
Yeah.
hyperparameter here, the length of this.
Yeah. Well, I mean, it's probably the height. Actually, it's the
That's
height.
the height? Oh,
Yeah, it's the height. If you think about it,
okay.
the bigger thing is, n by n in the input. So it's the
Got
bigger
it.
the bigger one. Yeah.
And then my next question is the choice here. That's also a hyperparameter.
Yeah, and that's going to be, height by, so yeah.
Yeah.
Yes. Yeah, and that's affecting these. I don't know if you can see my cursor. That's these. So these things here. Yeah. So it's height by width. Height by width. If you were to look up, this neuron connected to this, you could do it by going, down and along, and that would give
Yeah.
you that particular weight. And then obviously it's 10 because we have 10 digits, and that's what determines the output.
Okay. And then did you just play around with a few different ones to figure out which one trained the best?
Yeah,
Or did you?
something like that. Yeah, I think so. And also for visualization purposes and so on.
Very cool. So
So
what percentage are we at here? Is this like 80% or something?
Oh, yeah, from the notebooks, that's correct. Yeah, we got around 80%. And you could probably do better with convolutions. We didn't look at Boolean convolutions, but that's an option. That's something people have done. Yeah. Boolean conv layers.
Wait, can you explain what is a Boolean conv? So this
So
is
it's
just
so it's just in the same way a convolution is, some function that you're slicing the inputs and sliding it along, and it's basically the idea of shared weights. So you don't have independent sort of weights going to each thing. You're actually sort of reusing that weight value over and over and over again. That means that you're learning kind of local features. You're learning to detect edges and lines and combinations of lines. And I expect that would push you into the 90% category. Yeah.
so and then just to double check, is this using now backpropagation, using that Boolean?
It's using the same, Boolean backprop thing. But there's some other things going on behind the scenes, which is this. Let me just show you. Where do I have the notebook? Oh, actually, I've got some kind of working notebook. This kind of shows you that those layers are learning what sort of looks like features and combinations of features. So these are individual neurons and the weights that connect to the preceding layer, and you can see that it's learning kind of feature like things. And let me see, I had another notebook somewhere. Yeah, there was a lot on this one. Boolean nets, Boolean backprop. Oh, this was an early one. Okay, that's just a plot. No, I think it is this one. Somewhere I indicated like the result that we were getting, but not in this one. Oh yeah. Actually, this one got 90. This was like a 2-layer thing. Oh, and here's some earlier plots before it was neatened up for that video. Yeah. This is showing you the activations actually, not the weights.
Yeah.
Yeah. What was the point I was wanting to make here? There was something I wanted to say. Right. The convolution thing is probably something that would make it, competitive with real valued networks that we have. Yeah, I was playing around with batch norm. That's another thing. And the other thing is, there's this optimizer going on in the background, which is computing rolling statistics throughout the training. And you could say that these things are sort of like added complexity. But it's not clear whether the human brain or like biological brains don't do things like that. You know, they must have some capacity to accumulate things before making a decision, before making a change. They're not just making immediate changes in response to some stimulus. They're kind of waiting, building up some information. Maybe it might move in the other direction and suppress a change or so on, right? Because if you make a different change, then some change that you were kind of exploring as a candidate might no longer be valid, right? So that anyway, so that's why you need to keep this these statistics in the background. And there was, let me see, in I think it's this, yeah. So yeah, this is here kind of like the derivation of the chain rule and everything. This majority rule. Some kind of algorithmic description of the training loop. Oh, and you even have PyTorch implementation of these things if you want to try them out. Right, so you've got the backward pass, and it does it by just converting -1 and +1 to Boolean value. Well, assuming that -1 is false and +1 is true. Right, and this is the optimizer. So that's the point I was going to make, is that you need to keep these like rolling statistics. And when you exceed some threshold, which is indicated by this line here, that's when you decide which parameters to flip. So that's not clear from these visualizations, but it is going on behind the scenes.
So is that an activation? What is it? That's not an activation function though. Or what is
No,
that?
this is effectively an optimizer. So it's like, you know, Adam or
Okay.
SGD or something like that, but for Boolean neural nets. And all
And
it's
it's
doing,
not clear why how it's working or why it helps.
no, I mean it is clear because you need to account for like the local changes and global changes that are you know resultant of some bit flip that you make, some parameter change, right? Like if you change something, it's going to affect things downstream in the network. If you change things, you may want to avoid making sort of local changes on that layer
Yeah.
or suppress them, things like that.
Yeah.
So it's kind of motivated, yeah, by like Hebbian learning and other things like that.
So is it fair to say that's something like the global effect on a local change or something like that, like a local
Yeah,
derivative?
yeah.
The impact factor of a
Like you can avoid using this optimizer, but then effectively you're just doing gradient descent. Like you're not using like Adam or something. So it's like if you want momentum, you have to accumulate statistics. You have to keep track of like what direction you were going on the previous step and so on. But it actually, yeah, it does some other things. So like for example, whenever a weight changes, the statistics that are being accumulated reset to 0. So you kind of, yeah, you're sort of resetting and then you're letting your inputs flash through the network. You're accumulating things until some threshold is exceeded, and then you make a flip to the parameter. And you might come back and flip that parameter again, but this also allows you to kind of lock in and freeze a parameter because this accumulator might move in the other direction, right, and sort of oppose the change. Yeah. So it's basically identifying like where you have wiggle room, where you want to lock things in. It's allowing you to accumulate statistics over multiple mini batches. Yeah. And whenever a change is made, it's resetting those statistics so that the neuron is sort of treated as fresh, and you start accumulating those statistics from scratch.
And if
from
you
that
change
point.
back, then you lose the statistics again.
Yeah,
Or
yeah. You kind of
okay.
because you can only accumulate them with respect to like what the value is
Currently.
now. Yeah, currently, yeah. And you don't know how it's behaving until you assess the new value.
Yeah.
Yeah. So
Yeah.
yeah. Let's see. I think that's kind of most of what we covered. Now I checked our sort of internal chat thing, and I had this message from Eric Parfit, and so this is kind of linking things back to hypergraphs. It's very cool. What he's done here is really cool. We've discussed this, but we never actually kind of tried it out. And there's many avenues to explore here, like for how you could look at evolving, mutating hypergraph rewrite rules to achieve some objective, to learn some function. And this is an initial attempt at it, and it's quite promising. So, he's kind of referencing the work we did in the article. He's introducing the reader to like rewrite rules that we're all familiar with by now. But then what he's doing is learning this function by encoding. I think he's just counting the number of vertices. But you could use some other metric, or you could learn. You could use rewrite rules themselves to derive some quantities. Get as creative as you like. But the
These
idea
aren't
being,
currently hypergraphs, right? Those are just normal graphs right now. Yeah.
right.
Yeah.
But essentially what he's doing is he's using the number of vertices as the value, and so the initial condition of the rewrite system is the input, and then the final condition after some number of steps is the output. So that's your F. Your F is like something like let's just say it more explicitly. It's like vertex count of Wolfram model of blah, evolved rule init and steps. But actually your init is like encode X. So that which gives you some graph, right? So then your F of X is, do you see what I mean? So it's like we're using rewriting, and we're sort of encoding our input into a graph. We're evolving the system for some number of steps which we decide. And that whole thing is a function, and we can evolve that by doing but actually the system he's got going on here is quite interesting. It's effectively a fixed order of rule applications. So it's saying we apply rule 1, rule 2, 1, 2, 1, 2, 2, 2, 2, 1, 1, 1 in this order, and that's our function. And you can think of it as being some kind of like a path through the multiway system, or some class or equivalence class of paths, right? So you could be at some vertex in the multiway system, some state, and this thing represents some sort of fixed class of paths that take you from all possible states in the multiway system to some other set, right? It's like that, like in terms of pre-image, image.
Like a pattern of updating.
Yeah, it's a fixed pattern of rule applications. Yeah. Instead of applying all possible rules, it's like you only apply rule A, then rule B, A, B, A, B, B, B. So that's a program.
Like a meta rule.
Yeah, it's like,
No.
yeah, and it's like I'm saying, if you're in the multi-way
It's a
graph,
pattern. Yeah.
if you're in a multi-way graph and you're at some particular vertex, it's basically saying just walk in some particular fixed path from there. I mean, effectively, it's like a program. Although at some points you see that a rule happens and it doesn't make a change, and that's fine. You just skip it, or you just move on to the next one. Yeah, it's like a null operation or whatever. So that's really cool. And
how did those emerge? Those null operations in here? Was that just because of the search that he did to get to something?
Well, it's just that given this initial condition, given the evolution history up to this point, that rule just doesn't match. That's all it's saying.
And it was training on something? It was training
Yeah,
on...
it's our function from the blog. So it's
okay, same thing. Wow.
Yeah, same thing. He has some scheme for encoding his inputs and outputs. Right, and then you just take your input, which becomes a graph. You run the system forward, and you get some graph out, and you decode that. So it'd be really cool to try
of a state and represent it as a hypergraph or graph or whatever.
Because you don't often work with graphs. You might, but you don't often. You might have a graph problem, in which case just stick with graphs. But you probably want some kind of encoding and decoding going on. But yeah, it's just using like hypergraph rewriting and stochastic evolution like we were doing before. So you have the same kind of fitness graph that's like making successive improvements and so on. Yeah, I think this is really cool. I think there's a lot to explore here. It's the first example of actually doing it, but it's something we had talked about, but hadn't actually done. So yeah, that's courtesy of Eric Parfit.
Oh.
Yeah, so I just like to shout that out. He sent me in some DM a few months ago, but yeah, and you can see it doesn't kind of fully. I mean, but whatever. This function is a bit tricky and kind of contrived. It'd be cool to try it on like the sine function, for example, something like that. And it depends on your choice of rule. Like you maybe want more. Like he's restricted to just 2 rules. Maybe you want more to choose from. Like there's no. So this principle of drilling down to simplistic models, like that, this approach that Stephen takes is good when you want to talk about fundamentals, but experimentally and practically, it's not always the best decision, right? Sometimes you do need a bit of wiggle room, a bit of complexity. It's all over nature. It's all over the machine learning literature. And I'm making the point that you don't need to just stick to 2 rules. You could have 10 or whatever. And then your program would be some list of those 10 rules in some order.
I mean, what another thing to think about would be, okay, you have this hypergraph, and you have or you look at a little region, and you want to analyze that for some sort of metric, and then say, well, if it's like this, do this rule, or if the metric is different. So it's like a per locale sort of way of deciding what to do.
Right. Yeah. I think there's like
can of worms on what you're describing.
Yeah, there's like a whole landscape of like an infinite landscape of things that you could do. You could have like labeled graphs, labeled edges. You could have complicated like conditional rules. But yeah, without adding complexity, it's just showing that we can compute functions just by exploring the space of walks in the multi-way system kind of thing. And we can think of those as like programs or like functions, because they're just mapping some sort of set of states in the multi-way system to some other set, right? Just like a function takes some domain and maps it to some other domain, some set to some other set, or elements from that set to element. Yeah. You get my drift. Yeah, it's cool. And there were some other things that we've gone on to do subsequently that we haven't like published yet, that I wanted to show. Do I still have them open? Yes. And this is to do with like self-replication. So it's we're still dealing with rewriting, but we're still sort of slightly biologically motivated. And we're looking for systems that produce behavior like metabolic networks, like the Krebs cycle and all of the complicated metabolic networks that an organism has and so on. And this notebook in particular is looking at strings, except we have little bags of strings, which you can think of like as a kind of chemical soup. But instead of matching on just one string, we have rules that sort of want to match on at least 2. So this rule is looking for an A somewhere and an AB somewhere else. And then it will write that A to AB and that AB to A. And actually, it's kind of like swapping, isn't it? And I call this like a translocation rule. It's like taking the A over there and the AB over there, like a crisscross kind of thing. And that's giving you this kind of cyclic behavior. You can think of it as rewrite rules that have disjoint components, like a hypergraph rewrite rule, which is not fully connected, with the restriction that the rule components need to match in independent components of the state. Like as if the rule parts need to match in sort of like separate universes or separate disconnected graphs. You can think of it that way. And that has been giving us this, this self-replication behavior, this cyclic behavior, and some more complicated things. If you add in multiple rules, you get these kinds of networks which have what looks to be like multiple intersecting cycles. So this has like AB goes to ABA, BBA goes to BAB. So it's like two of these translocation rules. And we get
So that's
some kind
the
of
first
more.
one is like the B going from the first A and transferring to the second, right?
Yeah, it's like we're just swapping.
Mm-hmm.
But these are two rules, right? So that's one rule, that's the other rule. So I'm calling these like NRA rules, like two rule on a four state,
Mm-hmm.
right? Yeah.
Or on a state of 4 strings.
Yeah, state of 4 parts, and these 4 parts are canonicalized. They're sorted so that so that it doesn't matter what position the thing appears in, kind of thing. And we can do this with hypergraphs, but in this notebook, we're just doing it on strings, just as a simple model. Here, I'm looking at sort of multiple rules. Was just exploring like what happens. Trying to find things that have many cycles. Looking at what happens when you combine the rules and you get this complicated thing here. This is just the above, but turned into a simple graph. Or what did I do? I made the edges undirected to get rid of the double, bidirectional. I mean, a lot of chemical reactions are reversible, and obviously these rules are reversible. So the double edge is kind of annoying. So yeah, I got rid of it here, and we get something like this, which is some kind of metabolic network where you can move around these different paths inside it. Yeah, there's all sorts of intersecting cycles going on. We still have to do some more exploration on this, so that's kind of happening in the background. And then where I've taken that beyond is this multi-way chemistry. So using the chemistry functionality in Mathematica, which is basically just using molecule pattern, molecule plot, and pattern reaction, which is, so you can think of these as like graph rewrite rules, but now we have more annotation to the graphs. And so the rules are conditional. This is equivalent to like a blank, for example. But this must match an O with an implicit H. And the rules can, for example, be constraints on the valence of a particular bond and so on. Right. So that it's a bit more than just structural. It has some like semantic stuff on the graph, right? It's not just syntactical. This is so already we're seeing that like it's quite cool. So basically the idea here is like you list a bunch of reactions, like in my other notebook I've got it. So yeah, it's on this theme of like biology and machine learning, I guess, or biology. So we have like autoionization, alkene to alcohol, the Diels-Alder reaction. We have this big set of reactions, and then we can study them by just putting them in this multi-way chemistry function, put in a bunch of reactions, give our beaker full of chemicals, and then see what the resulting multi-way system would look like. So yeah, there's still work to be done here, but this is just a sneak peek at what's coming. Specifically for self-replication and yes, looking at minimal models of self-replication.
Yeah, so I was going to ask, what's the self-replication part here? What's how is it?
Well, that's really to do with
looking for autocatalytic cycles.
Yeah, that's right. Yeah,
loops in this space.
Yeah, so it's like kind of like closed time-like curves or something. You can think of it. It's like, and actually, Stephen asked about causality, and I'm in the past few days scratching my head, like, what does causality mean in a graph like this? Because this kind of causes itself, if that makes sense. It's like there isn't a.
it's a local property, right? So
Mhm.
so look, locally there's still a well-defined sense of causality, but globally you get some weirdness.
Yeah. It's a weird closed time like curve type thing, I think. It's like they're all interdependent. This thing causes itself, but also causes all of its descendant states, and every other state is equivalent.
Like an or like it's an ergodic state or something.
Mm.
Like an ergodic system.
No,
It's
But
like a
how-
little.
I wouldn't say so. I would think more of a equilibrium system or a oscillating system, something like that. Right?
oscillating.
Like, yeah, like a time crystal type thing. It's like a part of a multi-way system which is recurring, where the rest of the system can do all sorts of non-recurring things, but there are these patches which have like time crystal-like behavior. I think it's something like that.
So how is this replicating? Maybe I'm not understanding what the
Okay,
thing
actually,
is.
yeah. Right. Let me pull up another thing for that then. Let me see. Because yeah, you're right. It's kind of more like recurrence, like a Poincare recurrence type picture. Wait, I had a better one. This will be maybe a bit more intuitive. You could think of something like this as more like replicating, because this is an initial state in a CA, and then it's duplicating itself at some later point in time. So that's more like, it has children.
Yeah.
Yeah. Whereas um autocatalytic things are just survival of the individual. Something like that. Keeping itself around, keeping itself alive, not getting entangled with the rest of the environment and like subject to the laws of thermodynamics and so on. It's like, can you keep rebuilding yourself? Can you? And the way Stephen put it was like, you've got all these chemicals, they get kind of pulled into this attractor basin, which is your metabolic network. Like all the things you eat, all the energy that kind of comes into your body is coming through all of these reaction networks, but eventually finds itself kind of locked into these cycles and moving along these different paths. Because let's see, human metabolic network, or metabolic thing, like where's a good picture of that? There was one. I can't spell. Did I? Okay, like something like this. So what I've got on that notebook with the cycle is just we've created one, and we're kind of trying to find more complicated examples. Yeah, and we
Well,
want to.
I've never actually looked at this before. This is pretty cool. So what's the input? Is that like food? Or is this just like
Look,
energy?
we've got light,
Oh, there on the
oxygen,
left. Okay.
VO2, ATP, and then but the citric acid cycle, that's the Krebs cycle. That's kind of like the only one I really know.
Yeah, search for
But
metabolic pathways and you'll get like the big one.
Ah.
The big one.
Yeah. That's what I was looking for. Thank you. Yeah, I was looking for, because that one was a very simplified picture. Let me see. There is one that's like really dense, and I can sort of see. Oh, right, like this. Yeah. Okay. Cookies. Yay. Oh, it's just a background on a page.
Cookies are good for metabolism.
Yeah. Cookies are a vital part of the metabolic network. Okay, please. Okay.
The central part.
All right. Well, whatever. This we don't have to zoom in. We're just going to get like bewildered by complexity anyway. But there you go. If anyone finds one, do link it in chat, because I'm sort of not finding one very well.
Yeah. So the idea in my mind is like you had this primordial.
Try that one below. It might be higher res on the right.
Sorry, Dugan, you were saying.
Yeah. So like a small catalytic cycle
Mhm.
between a few like smaller molecules might produce in its process like a bigger molecule that hasn't been like made yet, and then now that
That's
gets
right.
like involved in whatever chemical
Mhm.
reactions that it can be involved in, and it complicates the
Yep.
story. So you have
Yes.
like small metabolic chain reactions, loops, get sized up with the introduction of new chemical.
Definitely.
And so these things sort of, the big ones evolved out of smaller ones. The big cycles evolved out of smaller cycles over the course of like more stuff happening.
Yeah, like building theorems from lemmas and so on. It's like we have this hierarchy of things, and there's a foundation, like these simple reactions, which are, as you say, producing end products which interact and form. Yeah, I mean that's kind of the story of, or one way of looking at the story of our existence, our
And then you
lives.
have, polymerization, just like,
Yep.
oh, this one thing just kind of knocks something off the end of this big long molecule and attaches the next piece to it.
Yep. Yeah, and it's early days. I think that I need to sort of improve this. I've just got the kind of early part of it. One thing is like, so I want to actually implement like the Krebs cycle, but you have to be a bit careful with the rules, because otherwise you keep having to introduce like what would be considered solution. Like, for example, you need to always keep a water around, like at least one water in your tuple, in your like little state bag thing, because these states are not necessarily single molecules. They can be multiple molecules, just like our strings are two states. Sorry. Yeah, just like our strings are, that you have multiple things in your like beaker. So what I think you need to kind of engineer the rules such that you don't need to explicitly keep inserting water, if that makes sense. So the rule assumes that water is always around, or hydrochloric acid is always around, kind of thing.
Yeah.
So we need to find somebody in our network that is familiar with the chemistry functionality and also has a background in chemistry and some biology as well.
Yeah,
Who can
that's actually a cool.
Yeah, because in the documentation, a lot of these rules are specified as, in fact, if I just find, just give me one sec. Let me just go to the document.
While Richard is putting that up, I just wanted to mention that explicitly that we are looking for somebody with probably around the postdoc level with specific experience in biology. And if you go to our website under the people section, there's a description of that position that we're opening up now. So if anyone wants to apply, just go to our website, and I would love to have a look at your experience and see if you can join the team.
Nice. Yeah, some of the reaction rules are specified using these smarts, which is like a kind of string encoding of, for describing molecular patterns. So they need to sort of find these reactions involved in known biological metabolic networks and encode them, and then transcribe them into the rule form where it's indicated, like the vertices have identities, and there's this morphism from left hand to right hand side and so on. So that's work that needs to be done if we actually want to show a concrete example of these autocatalytic reactions in known biological systems. Because right now all I'm doing is just taking reactions from the documentation. So yeah, we really need somebody to write these for the 8 reactions from the Krebs cycle. That would be really cool.
Octet something in biology.
Sorry?
There's some octet reaction.
Right.
Something. I saw something.
Right. But like Krebs cycle, citric acid cycle, it has 8 steps. It has 8 reactions, but like 10 steps, right? But it has 8 unique reaction categories or types, that are involved. So we need dehydration, we need hydration, oxidation. I mean, some of these are probably trivial and I could do it, but then for like some of the more complicated ones, it might not be so easy. And it needs the domain knowledge that I just don't have. So yeah, and then you know, working with us, then we can transcribe it into this rewrite. So this is a smart string representation of a, you know, like a chemical rewrite rule. So it's describing the molecule, but then it has the annotations. These indices here are, I think, effectively implementing this left-hand side, right-hand side sort of morphism, right? So it's associating this carbon with this on the right, this oxygen with this oxygen on the right. The double arrow is dividing the left-hand side and the right-hand side. The dot is separating the two reactants, which are on the left. And yeah, these are the smart string descriptions of the molecules with the annotations. It's a weird thing. Not everything is annotated. And then there's kind of implicit hydrogens. You know, there's so much hydrogen in the universe that it kind of sticks itself everywhere it can, kind of thing. Yeah, that's the idea. And I think
carbon, right?
Right. If it's not listed, it's carbon, and if it's not seen, it's assumed to be a hydrogen if there's a spare valence.
Just, hanging off.
Yeah.
Wait a minute.
But yeah,
there's a hydrogen hanging off oxygen.
I believe so, but I don't know.
Has two valences, right?
Right.
Okay, so both of those are used up.
Right. Okay. So it's just the inner, not leaf nodes. Right. Any unlabeled inner vertex is assumed to be a carbon from like organic chemistry kind of thing. Oh, cool. This highlight thing is actually really cool.
That is.
Yeah, that's really cool.
That's amazing.
Yeah, because you could sort of see, you can see which part corresponds to which. And I guess you could draw it with a graph with edges between the two. But yeah, you're right. I think that carbon shouldn't be hidden there, but I don't know. Like, I don't know. My dad was a chemical engineer. And it was the one subject I did slightly less well on than the others. I don't know why. It's kind of, chemistry's cool, but the actual mechanics of it can be a little bit boring sometimes, like figuring out. Yeah.
That reminds me of my final chemistry exam. I tried to grok the entire thing by drawing out every chemical reaction on this like massive sheet of paper.
Yeah.
And somehow by doing that, it like erased every possible memory of every chemistry equation I had. So it's not my thing.
But I was able to get, so for, like this one I added, so, you know, just by trying randomly, this intermolecular esterification and acetylation. And I took vinegar and alcohol, right? And with those two reaction types and those two products, we get some, actually, we don't get a cycle. I guess you get a cycle between two, but there's not like a larger cycle. But this was the first emergence of like something that's a bit more complicated. And I do have an example somewhere where I show you that the arity of the chemical bag changes. And that is happening in, I think 4. Yeah. Where is it? Yeah, some of these were pretty cool. Yeah, here, this one. So this one is the Oogie reaction. I don't know what that is. Don't ask me. It's in the documentation. You just go, yeah, acetylation and Oogie, and then like this thing, diethylmylate. You know, I'm just throwing everything together. Like, who knows what I'm making? Maybe I don't know. Maybe I'm making something illegal somewhere. I don't know. Sucrose, formaldehyde, diethylmylene, diethylamine. Right, but so with that quadruplet, 1, 2, 3, 4 of things, eventually it made some like tuplet thing. But has 2, but sometimes it's making 4 or sometimes 3 and sometimes 2. So it's kind of cool. And like these could be broken apart by some other reaction and we could get back to, you know, a 3 state. So starting from a 4, we could go to a 2 and then a 3 state. And it's like, yeah, kind of flexible.
But with the reactions that you specified, that it stops there, right?
It stopped here. This one had no more rules that applied. I think because at the summer school, I sort of recall that somebody gave a presentation, forget his name, on thing, and it looked like he was doing some kind of multi-way chemistry, and he might have done what I'm doing here, but in a better way or more informed. But this is just my initial attempt at sort of doing it myself.
So this is pre-biological. This is just raw chemistry.
Yeah, yeah.
So would something like the proton exchange at the mitochondrial level, would that be at the biological scale?
That's kind of like biophysics.
Yeah.
Whereas this is, yeah, like the mechanics of like metabolic systems. What you described there sounds more like, yeah, like a kind of biophysical thing. But I mean, again, it's like everything is
Because that's the
involved in the
source of our
process.
metabolism at the end of the, or
Right,
the source of our energy.
right.
Yeah, so how does that fit in the metabolic process or pathway? Like, where do the mitochondria fit in? Is it like one of those things on that very, very convoluted graph we saw earlier, or is it at a different
I'm sure it's
layer
listed.
level?
Yeah, I mean, if it is, and it probably gets into like ATP and things very
ATP
quickly.
stuff, yeah.
What did you
Okay.
call that? You called it the proton exchange. What did you call that?
In the mitochondria?
Potassium proton exchange protein. So it's like a protein.
Potassium pump.
Cool. So it's got some kind of gradient going on. They got electrochemical proton gradient across the inner mitochondrial membrane is used to drive ATP synthesis, right? Okay. I mean, yeah, it's just like the proton.
It's an
What is
interesting area of study.
It's
Yeah.
just a hydrogen that's ionized, right? So
Uh,
it's just ionized hydrogen. A proton, like hydrogen, is just a charged proton.
Yeah.
So
Yeah.
it's
So
still
hydrogen,
it's still
take off the electron, you just have a proton left. So it's ionized
exactly, yeah.
hydrogen.
Yeah. So we haven't really gone below chemistry, but yeah, it's electrochemical. It's like I guess electrobiological.
Interesting. So it's going like higher to the biological level, but then also going lower at the same time because it's like some kind of physics thing
Yeah.
happening. Yeah.
Yeah, like straddles multiple levels of this abstraction or whatever that we're looking at.
Yeah, it's a small side quest, but it's kind of relevant to the line of research that we potentially want to take at some point in the biology research that we're looking to do more of.
Yeah.
So anyway, just thought I'd mention it. This is really cool, Richard.
Thank you. Yeah, thanks. Really fun to go through it together with you all.
Yeah, this is what would have happened if we'd all taken a slightly different biological evolutionary pathway several millennia or million years ago. I would have been a cat.
I don't know what you're talking about. We were using human avatars before. We just turned them off, and this is actually us. I don't know about you.
Yeah, that was very cool, Richard.
Thanks, Carlos.
Appreciate it. Cool. Okay. Thanks so much, everyone. By the way, just gonna mention this. We have the winter school coming up on 6th of January. So registrations are open. Please sign up for that. Again, you can also find that on our website under community, I believe, right at the bottom, apply for winter school. And yeah, book club is still going nice and strong. Join our Discord. There's some interesting discussions happening. And tomorrow, I believe we're doing another live stream. Yeah, so tune in for that one. Cool.
Yeah.
All right. Thanks, everyone. I'm waving, but my avatar doesn't capture that.
Waving as well. Bye for now, guys.
Okay, bye.
Yeah. Cheers.
Bye.